A galaxy spins in the void, shaped like a perfect cosmic bullseye. This is the Cartwheel Galaxy, one of the universe's most bizarre and beautiful accidents. By the end of this journey, you will understand 50 of its strangest secrets, revealing how cosmic violence births celestial wonder. We will explore why its heart is missing, what monstrous black holes lurk in its brilliant ring, and how it shows us the chaotic infancy of the cosmos itself. What does such a radical transformation tell us about beauty in destruction? Its most famous feature is a ring of brilliant blue light, a perfect cosmic bullseye floating in the darkness. This is not a gentle, static halo. It is a shockwave, a tsunami of creation hurtling outwards from a cataclysm that reshaped an entire galaxy. Picture the calm surface of a pond. When a single stone is dropped into its center, ripples expand outward in perfect circles, disturbing the water as they travel. Now, replace the stone with a smaller, dense galaxy, and the water with a majestic spiral galaxy. Hundreds of millions of years ago, that is precisely what happened. The intruder did not hit the edge. It plunged directly through the heart of the larger spiral, like a bullet through an apple. The gravitational punch of this direct hit sent a colossal wave of gas and dust racing outward from the center at incredible speeds. This wave is the ring you see today. As it travels, it compresses the vast clouds of material in its path, squeezing them until they ignite into billions of new stars. The brilliant blue hue of the ring is the telltale signature of these stellar nurseries, where massive, hot, young stars blaze to life. So that perfect ring is not a peaceful structure. It is the propagating front of a cosmic explosion, a frozen moment of violent rebirth where destruction directly fuels the most spectacular creation. This wave of star formation is so intense it has a special name, a starburst. In a normal galaxy like our own Milky Way, stars are born at a steady, gentle pace. But in a starburst galaxy, the process is frantic and explosive, with thousands of stars igniting all at once in a cosmic frenzy. The Cartwheel Galaxy is a textbook example of this phenomenon, its brilliant ring a perfect laboratory for studying stellar birth on a truly epic scale. The physics at work here are both simple in concept and staggering in scale. As the gravitational shockwave races outward, it does not just push material aside. It herds it, piling up vast clouds of hydrogen gas and cosmic dust like a bulldozer, creating a massive berm. This compression is the critical trigger. Inside these now dense clouds, pockets of gas begin to collapse under their own gravity. As they collapse, they heat up. When the core temperature reaches millions of degrees, nuclear fusion ignites and a new star is born. This is happening on a colossal scale all along the leading edge of that ring. The ring itself is incomprehensibly vast, stretching for about 150,000 light-years from one side to the other. That is nearly 50% larger than our entire Milky Way galaxy. And this wave of creation is not standing still. It is racing outward from the galactic center at a speed of over 200,000 miles per hour. At that rate, the front of this stellar tsunami is traveling the distance from Earth to the Moon in less than 2 hours. So what we are witnessing is not a static picture. It is a snapshot of a dynamic, ongoing event, a runaway chain reaction of star birth that has been propagating across the galaxy for hundreds of millions of years, turning a single act of cosmic violence into a prolonged spectacle of light and life. But this brilliant ring of creation circles a profound emptiness. At the very heart of the Cartwheel Galaxy, where you would expect to find a dense, glowing knot of ancient stars, there is instead a puzzling void. Most spiral galaxies, including our own Milky Way, possess a bright central bulge, a crowded stellar metropolis where billions of older, yellower stars orbit in a tight sphere. The Cartwheel has almost none. Its core is faint and diffuse, a ghostly center that makes the entire structure look less like a classic spiral and more like a celestial donut. This missing bulge is the second great strangeness, a direct clue to the violence of its past. The galactic collision did not just trigger a wave of new stars, it effectively erased the galaxy's old heart. When the smaller intruder galaxy shot through the center, its immense gravitational force acted like a cosmic wrecking ball. It did not merely pass by, it violently stirred the galactic core, scattering the ancient stellar population that once formed that prominent bulge. The orderly orbits of billions of stars were thrown into chaos, flung outward or sent into elongated, chaotic paths that diluted the core's density. What remains is a scattered, disrupted region, a pale echo of what was once a brilliant central hub. This relative faintness is startling when compared to the ferocious blue glow of the outer ring. It creates a stark visual contrast that defines the Cartwheel's alien appearance. The galaxy's beauty is literally hollow at its center, a reminder that the very event which ignited its spectacular ring of youth also gutted its ancient soul. This ghostly center is not entirely isolated from the brilliant ring. Look closer and you will see faint, shadowy lines stretching from the inner hub out to the luminous blue circle, like the spokes of a vast cosmic wheel. These are not an illusion, they are real structures, the third great strangeness of this galaxy. While the ring blazes with newborn stars, these dark spokes whisper of what came before. They are the ghostly skeleton of the galaxy's original form. Before the catastrophic collision, the Cartwheel was likely a majestic spiral galaxy, much like our own Milky Way, with sweeping arms of stars and dust curling around its bright center. When the smaller galaxy punched through, the gravitational shockwave did not erase these arms entirely. Instead, it stretched them, pulling them outward and distorting them into these long, radial filaments that now bridge the old heart and the new ring of fire. They are cosmic scars preserving a memory of the galaxy's past architecture. Within these spokes, you find a very different population than in the ring. Here, the stars are older, cooler, and yellower. You also find dense lanes of cosmic dust, which appear as dark ribbons against the background glow. This dust is the leftover building material from an earlier era, now caught in these skeletal structures. Visually, the contrast is stark. The bright, almost electric blue of the newborn starburst ring sits against these dim, grayish spokes, creating a celestial image that is both beautiful and haunting. It is as if we are seeing two galaxies in one, the vibrant new body superimposed over the faint, stretched phantom of its former self. These spokes are a direct link, a bridge in time connecting the violent event of the past to the radiant result we see today. They remind us that even in the most radical transformations, echoes of the original form persist if you know where to look. But even that faint, hollow core holds another surprise. It is not centered perfectly within its brilliant ring. If you draw an imaginary line through the middle of the luminous blue bullseye, the galaxy's actual nucleus sits noticeably off to one side. This is the fourth strangeness, a subtle misalignment that betrays the sheer violence and chaos of the original event. A perfectly symmetrical collision, a direct hit from a perfectly aligned angle, might have left a centered core. But the universe rarely deals in perfect symmetry. The most likely explanation is that the smaller galaxy did not strike a dead center bullseye. It came in at a slight angle, delivering a gravitational blow that was heavier on one side than the other. Think of it not like a stone dropped into the center of a pond, but like a pebble thrown in at a sharp, glancing angle. The ripples it creates are not perfectly concentric, they are lopsided, stronger on one side. This asymmetric punch would have shoved the entire galactic core off kilter, sending it drifting from its original position even as the shockwave of star birth expanded outward in a more uniform ring. Another compelling theory involves the intruders themselves. We see not one but two smaller companion galaxies near the Cartwheel. Their relentless gravitational tugging, both during and for hundreds of millions of years after the collision, could be slowly pulling and twisting the core out of alignment, a continuous cosmic dance that prevents the galaxy from settling into a neat, symmetrical shape. This off-center heart is a crucial clue for astronomers. By measuring the exact degree of the offset and modeling the gravitational forces at play, they can work backwards to reconstruct the angle and the speed of the cataclysmic impact. It turns the entire galaxy into a forensic crime scene, where a single detail like a lopsided core can reveal the trajectory of a projectile that struck over 300 million years ago. The result is a celestial object that feels inherently unsettled, a wheel wobbling on its axle, a permanent testament to an impact that was anything but clean. Hovering near this lopsided wheel are two smaller galaxies, often framed in its iconic portraits like cosmic accomplices caught at the scene. These are the twin intruders, and they hold the key to the Cartwheel's past and its future. The smaller of the two, a compact galaxy seen below the ring, is widely considered the primary culprit, based on its trajectory and the forensic evidence left in the Cartwheel's structure. Astronomers believe this is the dense bullet that shot through the galactic core hundreds of millions of years ago, triggering the entire cataclysm. The larger companion, positioned above the ring, likely played a different role. It may have been a bystander, gravitationally bound to the main spiral, or perhaps it even helped guide the smaller galaxy on its destructive path. They are not mere spectators now. Both galaxies remain locked in a slow, gravitational dance with the wounded Cartwheel. Their persistent tidal forces, like invisible hands, continue to pull and twist at the galaxy's delicate structure. They tug on those faint, dark spokes, they subtly distort the brilliant ring, and they may even be funneling fresh supplies of hydrogen gas into the system. This ongoing interaction is crucial. The initial starburst-ring, for all its fury, will eventually run out of fuel. The gas compressed by the shockwave will be either turned into stars or blown away by stellar winds and supernova explosions. But the gravitational nudges from these companion galaxies could be channeling new reservoirs of cold gas into the Cartwheel's outer regions, potentially seeding a second wave of star formation long after the first ring fades. So the story is not over. The collision was not a single, finished event, but the opening act of an enduring celestial relationship. These twin intruders, one the attacker and the other its possible partner, continue to shape the galaxy they helped create, ensuring its evolution remains an active, unpredictable drama written in gravity and light. The brilliant blue light of the newborn stars is only part of the story. Hidden within that luminous ring are points of energy so intense they defy conventional explanation, the sixth strangeness, ultraluminous-xray sources. These are not stars as we know them. They are cosmic lighthouses beaming out not invisible light but in powerful, piercing X-rays, and each one shines with the ferocious brightness of millions of suns. A typical stellar mass black hole formed from a collapsed star might emit X-rays as it pulls gas from a companion, but its brightness has a theoretical ceiling, a limit defined by fundamental physics. The ultraluminous-xray sources in the Cartwheel Galaxy blast through that ceiling with ease. They are hundreds, even thousands of times brighter than any ordinary stellar black hole should ever be. This presents a thrilling puzzle for astronomers. What cosmic engine could possibly produce such outrageous power? One compelling answer is an intermediate mass black hole. We are familiar with stellar mass black holes weighing a few times our sun's mass, and supermassive monsters anchoring galactic centers weighing millions or billions of suns. The intermediate mass black hole is the long-sought missing link, with masses ranging from hundreds to hundreds of thousands of solar masses. An object like that, lurking in the star-forming ring and greedily feeding on the abundant gas there, could easily explain the incredible X-ray output. Another, even more exotic possibility is that these are stellar mass black holes operating in an extreme mode, a state called super-Eddington accretion. Imagine a black hole not sipping gas from a companion star, but rather gorging itself on a torrential, chaotic downpour of material from the surrounding stellar nursery. In this frenzy, the infalling gas becomes so dense and hot that it creates a thick, puffy envelope around the black hole, a kind of cosmic pressure cooker that allows radiation to push out with unimaginable force, breaking the normal brightness limits. The very fact that these ultraluminous-xray sources are found embedded within the Cartwheel's violent ring of starbirth is the crucial clue. The cataclysmic collision created the perfect environment for them, compressing vast amounts of fuel and triggering the rapid formation of massive stars that live fast, die young, and leave behind dense remnants ready to feast. Each ultraluminous source is a signpost, marking a spot where the galaxy's recent trauma has concentrated power into a single, voracious point, a direct and energetic consequence of the cosmic violence that reshaped everything. These ultraluminous-xray sources are not the only monsters born from the chaos. Scattered throughout that luminous blue ring, like diamonds sewn onto a celestial bracelet, are dozens of impossibly brilliant knots of light. These are super-starclusters, the seventh strangeness, and they are the true powerhouses behind the galaxy's radiant glow. Each one of these compact objects is not a single star, but a dense city of hundreds of thousands of stars, all born together in the same frantic burst of creation. To grasp their scale, consider Westerlund 1, a famous super-star cluster in our own Milky Way. It is one of the most massive young clusters we know, home to some of the largest stars ever discovered. The clusters in the Cartwheel Galaxy are like Westerlund 1 on cosmic steroids, born in an environment of far greater violence and abundance. They are the foundational factories of the entire starburst. When the gravitational shockwave compressed the galaxy's gas, it did not create stars evenly. It created these intense, localized pressure cookers where star formation went into overdrive. Within these nurseries, stars are born so close together that their mutual gravity binds them for billions of years, creating these glittering, permanent monuments to the collision. But their influence extends far beyond their own borders. The stars inside these clusters are not ordinary. They are predominantly massive, hot, and short-lived. These stellar giants flood their surroundings with an intense torrent of ultraviolet radiation. This invisible light is the key to the ring's iconic glow. It slams into the vast clouds of hydrogen gas that still permeate the ring, energizing the gas atoms and causing them to fluoresce, to shine with that characteristic ethereal blue and pinkish hue we see in telescope images. So the ring's beautiful luminosity is not just the combined light of billions of stars. It is the radiant echo of these superclusters, their fierce energy painting the surrounding cosmos. They are both the product and the engine of the starburst, concentrated points of extreme physics where the galaxy's traumatic rebirth is focused into dazzling, temporary beacons. Yet the story of this cosmic collision extends far beyond the brilliant ring and its dark spokes. Surrounding the entire Cartwheel Galaxy is a faint, ghostly glow, an immense and diffuse outer halo of stars. This is the eighth strangeness, a vast cloud of stellar refugees flung into the darkness by the violence of the impact. While the ring captures all the attention, this halo tells a quieter, more ancient tale. It is composed of billions of stars that once belonged to the original spiral galaxy, stars whose orderly orbits were shattered when the intruder blasted through. The gravitational chaos acted like a cosmic slingshot, hurling them outwards at tremendous speeds, scattering them into a vast, spherical cloud that now envelops the entire system. These stars travel on lonely, elongated paths that carry them hundreds of thousands of light years from the galactic center into the cold emptiness of intergalactic space. They are the lost population, forever separated from the dense, vibrant communities of the ring or the core. To our telescopes, this halo appears as an incredibly faint, uniform mist, a challenge to observe against the blackness of the cosmos. But it holds forensic gold. By carefully mapping the distribution and motion of these exiled stars, astronomers can perform a kind of gravitational archaeology. The pattern of the scatter is not random. It is a direct record of the forces unleashed during the collision. Think of it like analyzing the spray of debris after a massive explosion. The way the placement of each fragment reveals the point of origin and the strength of the blast. By tracing the paths of these halo stars backwards through time, scientists can reconstruct the precise angle and ferocity of the intruder's punch. Furthermore, by counting these stars and estimating their total mass, they can peer back before the catastrophe, piecing together the original size and heft of the majestic spiral galaxy that once was. This faint halo, then, is more than just scattered wreckage. It is a three-dimensional map of the disaster, a silent witness that allows us to weigh a galaxy that no longer exists and to measure the shockwave that tore it apart. The brilliant ring tells only part of the story of the galaxy's gas. Peering into the Cartwheel with radio telescopes, which see the cold, neutral hydrogen gas that fuels star formation, reveals a startling ninth strangeness. This primordial fuel is not neatly aligned with the spectacular ring of young stars. Instead, it is clumped in uneven clouds and appears to lag behind, trailing the luminous starburst in a ghostly, misaligned wake. This is the galaxy's hidden skeleton, and its arrangement is deeply puzzling. In a normal, undisturbed spiral, the hydrogen gas and the stellar population are closely intertwined, the gas nestled within the spiral arms where it condenses to form new stars. The collision violently severed this relationship. As the smaller galaxy punched through, its gravity did not just push a wave of gas outward, it also stripped and shredded vast reservoirs of hydrogen, pulling them away from their original locations and throwing them into chaotic new orbits. Some of this gas was caught up in the outward racing shockwave and compressed to form the brilliant ring, but a significant portion was left behind, either moving too slowly or flung into trajectories that did not sync up with the main wave. The result is a profound disconnect between where the stars are blazing and where the raw fuel for future stars currently resides. This misalignment is a critical clue for astronomers trying to predict the galaxy's future. The current starburst ring is feasting on the gas that was successfully herded forward, but what happens when that supply is exhausted? The trailing clouds of hydrogen represent a potential second act, a reservoir of fuel that could, over hundreds of millions of years, fall inward or be stirred up by the companion galaxies, triggering new rounds of star formation far from the current ring. This anomalous gas distribution paints a more complex, messier picture of the collision's aftermath, showing us that the cosmic violence did not create a clean, orderly result, but a system still very much in the throes of settling from the catastrophic blow. Within the brightest knots of the Cartwheel's ring, the starburst reaches its most extreme expression. These are the hotspot complexes, the 10th strangeness, where star formation is not just rapid but frantic and almost claustrophobic in its intensity. Each one of these brilliant knots is a sprawling metropolis of stellar birth, a region that could swallow entire star clusters from our own galaxy. They are so luminous that, from our distant vantage point, they often appear as single, blazing points of light, but they are in fact churning cauldrons containing dozens of the super-starclusters we discussed earlier, all packed into a relatively tiny volume of space. The scale is almost incomprehensible. A single hotspot complex can be over 1,000 light-years across, yet within that space, it is producing new stars at a rate that dwarfs the entire Milky Way galaxy. Our home galaxy forms about one new star per year on average. One of these cartwheel complexes can forge thousands in the same time. It is a stellar assembly line running at maximum, unsustainable speed, a direct result of the unimaginable compression caused by the propagating shockwave. These complexes are the ultimate laboratories for astrophysicists. They allow us to observe in a single, magnified view processes that are usually spread thinly across millions of light-years. Here, we can study how the most massive stars are born, how they immediately begin to blast their surroundings with fierce radiation and powerful winds, and how they die in spectacular supernova that seed the next generation. The conditions inside a hotspot are so extreme they likely represent the upper limit of how densely and quickly stars can form in the present-day universe. They are a glimpse into the chaotic, prolific conditions of the early cosmos, when entire galaxies flared to life in similar frenzies of creation. To witness them is to see the cartwheel's trauma focused into pinpricks of pure, transformative energy, where the galaxy is quite literally forging its future, one brilliant, volatile knot at a time. The sheer violence of these stellar nurseries carves immense voids into the very fabric of the ring. These are supershells and superbubbles, colossal cavities hundreds of light-years wide, blown into existence by the collective fury of the galaxy's youngest stars. Inside each of those brilliant hotspot complexes, dozens of massive stars are living fast and dying young. Their short lives are not quiet. From birth, they blast their surroundings with torrents of charged particles called stellar winds, which roar outward like continuous supersonic hurricanes. And when these giants finally exhaust their fuel, they do not fade away. They explode as supernova, detonating with the energy of billions of suns. When you have hundreds of such stars clustered together, their combined power does not merely stir the surrounding gas, it excavates it. The relentless stellar winds and the sequential shockwaves from multiple supernova push outward in all directions, sweeping up the interstellar gas and dust into a dense, expanding shell and leaving behind a vast, hollow bubble of million-degree plasma. Picture a single firecracker popping in a field of dense fog. It might clear a tiny space for a moment. Now imagine an entire string of dynamite detonating in sequence within that same fog. The result is a massive, cleared-out sphere, its walls rushing outward. That is the scale of a superbubble in the Cartwheel Galaxy, a temporary but monumental emptiness forged by pure stellar energy. These structures are not just cosmic curiosities, they are fundamental regulators. As a superbubble expands, its shockwave compresses the gas in the shell surrounding it, potentially triggering the next round of star formation along its rim. But simultaneously, the hot, empty interior acts as a barrier. It prevents the cold, dense gas needed to make new stars from flowing back into the central region, effectively shutting down star birth inside the bubble. So within the grand starburst ring, these superbubbles create a complex, self-limiting pattern. They are the galaxy's own feedback mechanism, where one generation of stars literally blows away the nursery that birthed it, carving out territories of future creation and permanent silence in an ongoing cycle of construction and demolition. But the visible light from those brilliant blue stars tells only half the story. Shift your vision to the infrared spectrum, to the light we feel as heat, and the Cartwheel Galaxy transforms into a blazing beacon of another kind. Its infrared luminosity is staggering, an 11th strangeness that reveals a hidden layer of its chaotic nature. While our eyes see the glow of newborn stars, infrared telescopes see the warm, dusty blanket that surrounds them. All that furious star formation within the ring is doing more than just producing light. It is also manufacturing immense amounts of cosmic dust. The massive stars flooding their surroundings with intense ultraviolet radiation, and the titanic supernova explosions that end their short lives are both cosmic foundries. They spew out heavy elements like carbon and silicon, which rapidly condense into microscopic solid particles, tiny grains of dust no larger than smoke particles. This dust does not stay near the stars that created it. It is blown outward by stellar winds and supernova shockwaves, filling the entire ring structure with a thick, opaque haze. And then it absorbs the very starlight that birthed it. The brilliant ultraviolet and visible light from the hot young stars slams into these countless dust grains, which soak up that energy, heat up to temperatures of -100 degrees or so, and then re-radiate it all back out as a deep, pervasive infrared glow. The sheer quantity of dust is mind-boggling. The Cartwheel Galaxy produces and contains more dust than entire normal galaxies many times its size. In fact, its total infrared output is so extreme it rivals the luminosity of some quasars, those incredibly bright cores of distant galaxies powered by voracious supermassive black holes. That comparison is crucial. It means the Cartwheel starburst-ring, fueled by a collision, is releasing as much raw energy in the form of heat as some of the universe's most violent and energetic objects. So the galaxy's true power is not just in the light we can see, but in the invisible thermal roar that surrounds it, a permanent afterglow of its traumatic and prolific rebirth. This hidden architecture of dark matter may hold the key to the ring's very existence. The violent collision that created the Cartwheel's luminous ring was not just a clash of stars and gas, it was a profound disturbance in its unseen dark matter halo. This mysterious substance, which makes up over 80% of the galaxy's mass, does not shine, absorb, or reflect light, yet its gravity is the cosmic glue holding the entire structure together. The cataclysm provides a rare and perfect laboratory to test our models of dark matter itself. When the smaller galaxy punched through, it did not just stir the visible material, it also plowed through this vast, invisible sea of dark matter, sending ripples through its very fabric. Astronomers can now use the aftermath as a forensic tool. By meticulously measuring the motions of stars within the ring and the faint outer halo, they can work backwards. They calculate how much gravitational pull is needed to keep those stars moving as they do, and then they subtract the pull from all the visible matter they can see, the stars and the gas. What remains is the gravitational signature of the unseen, a detailed map of the dark matter's distribution. The central question is profound. Does the dark matter halo now also show a ring-like structure, echoing the brilliant starburst we see in light? Or did it simply stretch and smooth out, absorbing the impact in a more fluid way? The answer depends entirely on the fundamental nature of dark matter particles. If dark matter is cold and moves slowly, as the most popular theories suggest, it would tend to clump. The collision could have sculpted it into a denser, ring-like shell aligned with the visible one, a ghostly twin to the starburst. If it is warm or interacts with itself in more complex ways, it might have simply flowed around the intruder, settling back into a smoother, more featureless halo. By observing how the visible ring propagates and comparing it to sophisticated computer simulations, scientists are essentially weighing and probing an invisible substance hundreds of millions of light-years away. Each star's path is a data point in this grand experiment, its orbit dictated by the hidden mass we cannot see. The Cartwheel Galaxy, therefore, is more than a spectacle. It is a cosmic-scale particle detector, its beautiful ring acting as a probe into the deepest and most mysterious component of our universe. The gravitational violence of that ancient collision flung more than stars into a faint halo. It also likely stretched and tore long, delicate ribbons of material directly from the galaxy's body, creating tidal tails. These are the cosmic equivalent of comet tails, vast streams of stars, gas, and dust pulled out by immense gravitational forces during a close encounter. In a dramatic galactic merger, these tails can be spectacular, arcing across hundreds of thousands of light-years. For the Cartwheel, the story is more subtle. Its iconic portrait shows no obvious, brilliant tails stretching into the void. This apparent absence is itself a critical piece of evidence. The formation of prominent tidal tails depends heavily on the geometry of the crash. A slow, grazing collision where two galaxies spend eons swirling around each other is excellent at pulling out long, graceful streams of material. But the Cartwheel appears to have been the result of a much faster, more direct punch. The smaller intruder came in at high speed, plunging through the heart of the larger spiral like a bullet. In such a rapid, penetrating impact, there is less time for gravity to gently pull material out into long streams. The violence is more concentrated, the energy transfer more explosive. focused on sending a shockwave through the disk rather than meticulously unraveling it. So the lack of obvious giant tails suggests a specific type of collision, one that was both swift and centrally aimed. However, the absence of evidence is not evidence of absence. With our most sensitive telescopes, astronomers continue to search for extremely faint, diffuse stellar streams around the Cartwheel. The discovery of even a wispy, broken tail would be a monumental clue. Its orientation would act as a frozen arrow pointing directly to the direction from which the intruder came. Its length and density would reveal the speed of the encounter. A long, thin tail implies a slower, more drawn-out gravitational tug. A short, stubby one or none at all reinforces the bullet theory. This search turns the empty space around the galaxy into a forensic canvas. Every photon of light collected from those dark regions is sifted, looking for the faint smudge of exiled stars that could map the precise trajectory of a catastrophe 300 million years old. Whether we find them or not, the answer writes a clearer line in the story, telling us exactly how the hammer fell on this galactic anvil. To truly see the Cartwheel Galaxy, you must look with more than just your eyes. Its visible light portrait, that perfect blue bullseye, is only one page of a much deeper story. Astronomers piece together its full history by observing it across the entire electromagnetic spectrum, capturing light our eyes can never see. Each wavelength band acts like a specialized filter, peeling back a different layer of this cosmic onion to reveal secrets hidden from the others. The iconic Hubble Space Telescope provides the breathtaking visible light view we know so well, showing the brilliant blue starburst-ring and the faint skeletal spokes. But switch to the Chandra X-ray Observatory and the galaxy transforms. The soft blue glow vanishes, replaced by dozens of brilliant, piercing points of light scattered throughout the ring. These are the ultraluminous-xray sources, those voracious black holes feeding in frenzy, and vast clouds of gas superheated to millions of degrees by countless supernova explosions. This X-ray vision shows us the galaxy's most violent and energetic processes, the searing aftermath of its stellar birth frenzy. Then turn to the Spitzer Space Telescope, which sees in the infrared. In this view, the blue ring dims, and instead a fiery, rust-colored glow emerges, outlining the same structure in a completely different light. This is the thermal signature of all that cosmic dust, warmed by the young stars until it radiates its own heat. Infrared light also pierces through that dust, revealing the cooler reservoirs of gas that will fuel future generations of stars, and even hinting at the distribution of older stellar populations in the faint core. The composite image that merges all these views is where the magic happens. The blue starburst ring, the pink X-ray hotspots, and the red infrared dust lanes all align, yet each tells an independent tale. This multi-wavelength approach is not just for creating pretty pictures, it is an absolute necessity for science. Without X-rays, we would miss the monster black holes. Without infrared, we would be blind to the fuel supply and the true scale of the dust-enshrouded chaos. Only by listening to the galaxy's full symphony of light, from the high-energy shriek of X-rays to the low-energy hum of infrared, can we begin to understand the complex, interconnected aftermath of a collision that rewrote an entire island universe. That brilliant ring is not a single, uniform band of light. It possesses a hidden gradient of age, a chronological record written in starlight. As the shockwave from the collision has expanded outward over hundreds of millions of years, it has not triggered star formation everywhere at once. Instead, it acts like a cosmic snowplow, compressing gas and igniting new stars only at its very leading edge. The result is a clear, observable timeline. The outermost rim of the ring, the part farthest from the galaxy's center, glows with the fiercest, hottest blue light. This is the current frontier, where the shockwave is actively plowing into fresh reservoirs of gas, and the youngest stellar nurseries, perhaps only a few million years old, are bursting into existence. Move your gaze inward just behind that brilliant leading edge and the color subtly shifts. The blue softens, tinged with more white and yellow. Here, the stars are slightly older, perhaps 10 to 50 million years. Their most massive blue members have already lived out their short, violent lives and exploded, leaving behind a population of longer-lived, less frantic stars. Continue further inward toward the galaxy's hollow core, and the stellar population becomes older still. These are stars that were born in the first wave of the starburst over 100 million years ago as the shockwave first began its epic journey. They have settled into a more mature phase, their communities stabilized after the initial frenzy. This age gradient is a direct and powerful confirmation of the entire collision theory. It allows astronomers to read the ring like the growth rings of a giant cosmic tree. By measuring the precise color and brightness of stars across the ring's width, they can chart the propagation of the starburst wave with remarkable precision. They can calculate not just how fast the wave is moving, but how the rate of star formation has changed over time. Was the initial burst more violent than it is today? Is the wave now running into denser or sparser gas clouds? The answers are encoded in this stellar chronology. This single feature transforms the cartwheel from a static snapshot into a dynamic movie, letting us witness the ongoing aftermath of the impact frame by frame, as the galaxy continues to write its own history in newborn stars. The starlight itself holds a chemical record of the galaxy's violent rebirth. By analyzing its spectrum, the unique fingerprint of light split into its constituent colors, astronomers can perform a kind of cosmic chemistry, identifying the specific elements present in the cartwheel stars and gas. This reveals the 17th strangeness, a peculiar and telling pattern of chemical abundances. In a normal, mature galaxy like our Milky Way, generations of stars have lived and died, polluting the interstellar medium with heavy elements forged in their cores and scattered in supernova explosions. This process, called nucleosynthesis, gradually enriches the galactic environment with elements like carbon, oxygen, silicon, and iron. The cartwheel, however, is a galaxy caught in the act of this enrichment, and the results are not uniform. The brilliant blue ring, the site of frantic new star formation, presents a fascinating chemical portrait. Spectroscopy shows it is indeed rich in the products of recent nucleosynthesis, particularly alpha elements like oxygen, neon, and magnesium. These are the classic signatures of massive stars that live fast and die in core collapse supernova, exactly the type of stars being produced in the ring's stellar factories. Their short lifetimes mean they scatter their freshly forged heavy elements back into the surrounding gas almost immediately on cosmic timescales, so the ring's interstellar medium is being actively and rapidly seasoned with these new metals. Yet there appears to be a relative shortage of iron. Iron is primarily produced in a different type of cataclysm, the thermonuclear explosion of a white dwarf star known as a Type I supernova. These events take longer to occur as they require a specific binary star system to evolve. The current starburst in the ring may simply be too young for these iron-producing events to have become common. The chemical signature, therefore, is like a snapshot of a specific moment in a recipe where some ingredients have been added in abundance while others are still waiting on the shelf. This creates a distinct chemical imbalance compared to the galaxy's faint core. That older, scattered heart, populated by stars that formed before the Great Collision, likely shows a more balanced, mature mix of elements, the result of billions of years of quieter stellar evolution. The contrast between the ring and the core provides a direct map of nucleosynthesis in action, showing us how different types of stellar explosions contribute their unique products to the galactic ecosystem at different times. It is a tangible record of how a single traumatic event can reset and accelerate the chemical evolution of an entire galaxy, forging not just new stars but a new elemental identity. The smaller intruder's fate is written in the arc of its escape, After delivering its catastrophic blow, this dense bullet of a galaxy did not stick around. It was flung away by the very forces it unleashed, now receding into the darkness on a long, looping path. But gravity is a patient author, and its story with the cartwheel is likely far from over. The critical question astronomers grapple with is the shape of that path. Is this a clean break, a hyperbolic orbit where the companion achieves escape velocity and sails off into intergalactic space forever, never to return? Or is it bound on a vast, elliptical orbit, destined to swing back in a few billion years for another, potentially devastating encounter? The answer depends on the precise speed and angle of that initial impact, variables we are still piecing together from the forensic evidence left behind. If the intruder is on a return trajectory, its next passage would not be a direct hit but a slower, more drawn-out gravitational dance. This would not create another clean ring. Instead, it would twist and warp the already delicate structures of the cartwheel, pulling those faint spokes into new shapes, stirring up the gas in the outer halo, and potentially triggering a second, more chaotic wave of star formation that overlaps the first. It would be a galactic renovation, adding layers of complexity to the existing masterpiece. If, however, the companion is lost forever, the cartwheel's future is one of slow, solitary evolution. The brilliant ring will continue to expand and fade as its fuel is exhausted. The starburst will quiet, the blue giants will die, and over billions of years, the galaxy will settle into a smoother, more placid form, a lenticular or irregular galaxy bearing the permanent scars of its youth. The intruder's trajectory, then, is a single variable that bifurcates the future into two radically different narratives, one of ongoing gravitational conversation and another of quiet, solitary recovery. Every observation made to pin down its exact motion is a reading of this celestial cliffhanger, a prediction of whether the next chapter will be a sequel of violence or an epilogue of calm. The super-starclusters blazing within the cartwheel's ring may be incubating the ultimate stellar catastrophe. These dense knots of frantic star birth are the perfect theoretical environment for creating long gamma-ray bursts, the single most powerful explosions known in the universe since the Big Bang. While we have never detected one within the cartwheel itself, the conditions there align eerily with what astrophysicists believe spawns these terrifying events. A long gamma-ray burst begins with the death of a very specific kind of star, one at least 40 times more massive than our Sun, spinning at a ferocious speed and stripped of its outer hydrogen envelope. This stellar monster must be a Wolf-Rayet star, a bare, blazing core nearing the end of its brief life. The super-star clusters in the cartwheel's ring are factories for exactly this type of star. Their dense, chaotic environments encourage the rapid formation of stellar giants, and the violent interactions between such closely packed stars can easily strip away a star's outer layers and spin it up to the required dizzying velocities. When such a star finally exhausts its fuel, its core does not simply collapse into a black hole. The rapid rotation focuses the collapse into two narrow, opposing jets of material and energy that scream outward at nearly the speed of light. If one of those jets is pointed directly at Earth, we witness the gamma-ray burst, a blinding flash of high-energy radiation that can outshine an entire galaxy for a few fleeting seconds. The cartwheel, with its hundreds of these extreme stellar nurseries, is statistically one of the most likely places in the nearby universe for such an event to occur in the future. It is a loaded gun, a cosmic landscape where the ingredients for the ultimate detonation are being assembled right now. To witness a gamma-ray burst from within such a spectacular ring would be a monumental event, a fleeting point of light that would momentarily drown out the glow of billions of stars, a final, spectacular signature of the galaxy's relentless, transformative violence. This frantic, all-consuming starburst is not a unique modern event, it is a cosmic echo. The Cartwheel Galaxy's furious rate of star formation provides a direct and precious analog to the most distant galaxies we can observe, those that flared to life in the chaotic infancy of the universe. Billions of light-years away, at the edge of our observational horizon, we see galaxies as they were when the cosmos was only a fraction of its current age. Their light, stretched by the expansion of the universe into a deep red, reveals a wild and violent epoch. These primordial galaxies were not the orderly spirals we know today. They were messy, irregular, and constantly colliding. Their defining feature was an incredible, almost reckless pace of star birth, driven by the abundant gas of the young universe and the frequent, violent mergers between smaller galactic building blocks. They were cosmic furnaces, forging the first generations of stars at rates that would dwarf even the most active regions of our modern Milky Way. The problem is, they are so incredibly far away that even our most powerful telescopes see them only as faint, blurry smudges of light. We can measure their overall brightness and estimate their star formation rates, but the intricate details, the internal mechanics of how that star birth proceeds, remain frustratingly out of focus. This is where the Cartwheel becomes an indispensable laboratory. It is a rare, nearby replica of those ancient processes. Here, in our own cosmic backyard, we have a galaxy undergoing the same kind of frenzied, merger-driven starburst that was commonplace over 10 billion years ago. Its ring, with its brilliant hotspot complexes and expanding superbubbles, is a close-up, high-definition view of the very engine that powered the early universe's construction boom. By dissecting the Cartwheel, by mapping how its shockwave compresses gas, how its superstar clusters form and evolve, and how its stellar feedback carves out space, astronomers can build a detailed template. They can then apply that understanding to interpret the faint, redshifted glow of those distant galaxies, reading their blurred light with new clarity. The Cartwheel is a time machine, not one that transports us, but one that brings a piece of the universe's frantic youth within reach, allowing us to study the chaotic birth of galaxies not as a distant theory, but as a vivid, ongoing reality. The immense dark matter halo enveloping the Cartwheel Galaxy is more than just invisible scaffolding. It is a potential cosmic magnifying glass, a gravitational lens of staggering proportions. This halo, containing most of the galaxy's mass, warps the very fabric of space-time around it, creating a subtle curvature. According to Einstein's theory of general relativity, light from a distant object traveling through this warped space does not follow a straight line. It bends. If a far more distant galaxy happens to lie directly behind the Cartwheel from our point of view, the halo's gravity can deflect and focus that background galaxy's light, distorting its image into arcs or rings, or even magnifying it, making the faint object appear brighter and larger to our telescopes. This phenomenon, called strong gravitational lensing, is a powerful tool used across the cosmos to weigh galaxies and clusters, but observing it with the Cartwheel presents a unique challenge. The galaxy's own brilliant, sprawling ring of starburst light is a formidable obstacle. It acts like a dazzling foreground street lamp, obscuring the faint, distorted glow of any potential background galaxies lensed by the halo. It is like trying to spot the flame of a single candle placed directly behind the blinding beam of a searchlight. Despite this difficulty, the potential reward makes the search compelling. If astronomers could successfully identify and measure a lensed image behind the Cartwheel, it would provide an independent and highly precise measurement of the galaxy's total mass, including every ounce of its elusive dark matter. This measurement would not rely on the motions of stars or models of the collision. It would come from the direct geometric effect of gravity on light itself. It would be a pure test, a way to cross-check all the other mass estimates derived from the galaxy's structure and dynamics. Finding such a lensed arc would be a monumental discovery, turning the Cartwheel's beautiful chaos into a precise cosmic scale, its hidden mass revealed not by what it emits, but by how it bends the light of the universe beyond. Its unique form makes it the defining member of a celestial elite, the Ring Galaxy. This is not a common shape. Among the hundreds of billions of galaxies that fill the observable universe, only a tiny fraction, perhaps 1 in 10,000, presents this perfect bullseye structure. The Cartwheel Galaxy is the archetype, the most dramatic and intensely studied example of this cosmic oddity. It is the textbook case, the one astronomers point to when explaining how gravitational shockwaves from a direct collision can sculpt a spiral into a ring. But it is not alone. Look at Hoag's object, another stunning ring galaxy discovered just a few years before the Cartwheel. At first glance, they appear as cosmic twins, a nearly perfect ring of blue young stars encircling a yellow, ancient core. Yet their stories diverge profoundly. Hoag's object shows no signs of a recent, violent collision. Its core is perfectly centered, and there is no evidence of a disruptive companion galaxy nearby. Its formation remains one of astronomy's beautiful puzzles, possibly the result of a slow, ancient accretion of gas or a complex internal instability. The Cartwheel, by contrast, is a story written in forensic detail. Its off-center core, its dark spokes, its twin companions all scream of a recent catastrophic impact. This comparison is crucial. It tells us that the universe can create similar cosmic masterpieces through entirely different processes, one a sudden, violent trauma, the other perhaps a slow, mysterious evolution. The Cartwheel stands out even among ring galaxies for its sheer intensity. Its starburst ring is brighter, its structure more complex, and its history more clearly decipherable than any other. It is the loudest, most explosive member of this quiet family, a living laboratory where the physics of galactic collisions and star formation are displayed with unmatched clarity. To study ring galaxies is to study the Cartwheel, for it remains the prototype against which all other cosmic rings are measured, the definitive example of how chaos can forge a perfect circle. But to truly understand the Cartwheel's violent past, we must not only observe it, we must recreate it. Modern astrophysics uses the most powerful supercomputers in the world to build virtual universes, running simulations of galactic collisions over and over to see if we can produce a perfect digital twin of our cosmic bullseye. These are not simple animations, they are complex mathematical universes governed by the laws of physics, tracking billions of particles representing stars, gas, and dark matter. Scientists input their best guesses for the initial conditions, the size and speed of the intruder galaxy, the angle of impact, and the properties of the dark matter halo. Then they press start and watch cosmic history unfold in a fraction of the time. The goal is to hit the bullseye, to produce a simulation that, after hundreds of millions of virtual years, looks exactly like the Hubble image of the Cartwheel Galaxy. The results are both stunningly accurate and revealingly imperfect. State-of-the-art simulations can now produce breathtaking ring galaxies with eerie similarity to the real thing. They recreate the expanding shockwave, the brilliant blue ring of star formation, and even the faint, ghostly spokes stretching inward. This success is a monumental validation of our core theories of gravity and galactic structure. It tells us we are fundamentally on the right track, that a direct, high-speed collision is indeed the engine behind this celestial spectacle. Yet the devil and the discovery is in the details. The most sophisticated simulations still struggle to perfectly match the Cartwheel's precise ring diameter, the exact distribution of its brightest knots, and the subtle lopsidedness of its core. These discrepancies are not failures, they are priceless clues. Each mismatch is a question posed by the universe, perhaps our models for how gas clouds collapse to form stars within the shockwave are too simple. Maybe the dark matter halo has properties we have not yet accounted for, interacting in ways that subtly alter the ring's propagation. Or perhaps the initial conditions were even more extreme than we assumed, with the intruder galaxy being denser or moving faster. Scientists then tweak their virtual universe, adjusting one parameter at a time, running the simulation again to see if the ring tightens, if the spokes become clearer, if the model snaps into perfect focus with reality. This iterative process is how astrophysics progresses. The Cartwheel Galaxy acts as a cosmic benchmark, a finished puzzle against which we test our incomplete picture of galaxy evolution. Every failed simulation teaches us something, refining our understanding of the chaotic interplay between dark matter, gas dynamics, and stellar feedback. It turns the galaxy from a static object into a dynamic test, a question written in stars that our most powerful computers are tirelessly working to answer. Magnetic fields are the silent architects within this chaos, invisible lines of force woven through the very fabric of the galaxy. While gravity sculpts the grand structure and radiation paints it with light, magnetism operates on a more subtle, pervasive scale, potentially directing the final details of creation. Within the Cartwheel's churning ring, where gas is compressed, stars are born, and supernova blast material in all directions. These magnetic fields are likely not passive spectators. They are being stretched, twisted, and amplified to extraordinary strengths by the sheer violence of the ongoing starburst. Picture the turbulent wake behind a speedboat where the churning water creates complex, interlocking swirls and eddies. Now imagine that each droplet of water carries a tiny compass needle, and the chaos of the wake forces all those needles to align, building up a powerful, organized force within the turmoil. That is a crude analogy for what may be happening in the ring. The shockwave's passage, the stellar winds, and the supernova explosions all inject immense turbulent energy into the interstellar medium. This turbulence can stretch and fold the galaxy's primordial magnetic field lines, effectively dynamoing them into a far stronger and more tangled web. The resulting magnetic pressure could be powerful enough to resist the gravitational collapse of some gas clouds, effectively propping them up and preventing star formation in certain areas, while guiding and channeling flows in others. This means magnetism might be drawing an invisible blueprint within the ring, determining which dense knots of gas finally collapse into superstar clusters and which are held apart. Observing this directly is a monumental challenge, requiring specialized radio telescopes that can detect the faint signature of synchrotron radiation, the glow emitted by electrons spiraling at near light speed along magnetic field lines. By mapping this subtle radio fingerprint across the Cartwheel's ring, astronomers hope to trace the invisible magnetic skeleton that underpins its brilliant facade, revealing whether these hidden forces are the final sculptors in the galaxy's ongoing rebirth. That magnetic web of energy may suddenly snap, releasing a flash of light visible across the universe. The Cartwheel Galaxy is a beacon for time-domain astronomy, the study of how celestial objects change and flare over time. Within its churning ring of stellar nurseries, the conditions are perfect for sudden, violent, and brilliant transient events. These are not the slow, steady glows of normal stars, but unpredictable cosmic fireworks, brief explosions that can outshine entire galaxies for days or weeks before fading back into darkness. The sheer density of massive, short-lived stars makes the Cartwheel a statistical powerhouse for such events. Supernova, the titanic explosions marking the death of stars many times more massive than our Sun, are expected to be almost commonplace here. Given the frantic star formation rate, astronomers estimate a supernova could detonate within the Cartwheel's ring as often as once every few years. Each one is a landmark event, a temporary new point of light that can be used to probe the conditions within the ring, measuring gas densities and elemental abundances in the expanding blast wave. But supernova are just the beginning. The galaxy is also a prime candidate for witnessing even rarer and more exotic transients. Luminous blue variable eruptions, for instance, occur when a hypergiant star, one of the most massive and unstable stars possible, undergoes a violent tantrum. Instead of exploding completely, it sheds a colossal shell of its own outer atmosphere in a paroxysm that can temporarily make it millions of times brighter than our Sun. These eruptions are previews of a coming supernova, offering a chance to study a star in its final, most volatile throes. To catch these fleeting moments, automated sky surveys like the Zwicky Transient Facility and the future Vera-C Rubin Observatory constantly scan the heavens. Their robotic telescopes take image after image of the same patches of sky, night after night, feeding the data into algorithms trained to spot any new pinprick of light. The Cartwheel, with its known high activity, is a priority target on their watch list. Every new flash from its direction triggers an alert, sending astronomers scrambling to point every available telescope from radio to X-ray toward the galaxy. Each transient event is a unique experiment, a chance to witness the extreme physics of stellar death and transformation in real time, using the galaxy's chaotic ring as both the stage and the catalyst for the drama. The data from the Cartwheel Galaxy can be heard as well as seen. Scientists have taken the observations from Chandra, Hubble, and Spitzer and translated them into sound, a process called data sonification. This turns the silent light of the cosmos into a haunting symphony of the collision, allowing us to experience the galaxy through an entirely new sense. The technique assigns distinct musical notes to different brightness levels and specific instruments to different wavelengths of light. The X-ray data from Chandra, revealing the searing hot gas and ultraluminous black holes, becomes sharp, penetrating chimes. The iconic visible light from Hubble, outlining the brilliant blue ring and the faint spokes, transforms into clear, resonant strings, and the warm infrared glow from Spitzer, emitted by all that cosmic dust, is rendered as a deep, atmospheric drone from lower-pitched woodwinds. As the piece plays, a radar-like scan moves outward from the galaxy's core. You first hear a quiet, sparse region from the faint, hollow center. Then, as the scan crosses the dark, skeletal spokes, the strings rise in a complex, layered pattern, mirroring the older stellar populations and lanes of dust. The crescendo arrives at the brilliant starburst-ring, where all three instruments, the chimes, the strings, and the drones, swell together into a dense, chaotic, and powerful chord. The areas of most intense star formation, the hotspot complexes, burst forth as concentrated clusters of high, bright notes, a sonic explosion within the larger symphony. This is not merely an artistic interpretation, it is a direct translation of scientific data into an auditory landscape. It reveals patterns our eyes might miss, the intricate interplay between the violent X-ray sources, the visible starburst, and the dusty shroud. To listen is to hear the galaxy's history performed, the quiet prelude of the old core, the rising tension of the expanding shockwave, and the roaring, sustained climax of ongoing creation. It is the sound of cosmic violence remixed into a form of beauty we can feel, a reminder that the universe speaks in a language far beyond visible light. The energy radiating from the Cartwheel's ring is so immense it cannot be contained. Phenomenon 27 reveals how this fury escapes the galaxy itself, as the combined might of stellar winds and supernova explosions does more than sculpt superbubbles. It can launch colossal fountains of million-degree gas clear out of the galactic disk. This process, known as a galactic superwind, acts like a cosmic pressure valve. Picture a pot of water boiling over on a stove where the steam billows up and spreads across the ceiling. In the Cartwheel, the continuous detonation of thousands of massive stars creates a similar, unimaginably powerful overflow. The hot plasma from countless supernovae merges into a single, raging torrent that punches through the galaxy's thinner outer regions, carrying with it heavy elements freshly forged in stellar cores. This superwind streams out above and below the plane of the ring, carrying energy and chemically enriched material far into the galaxy's halo and beyond. Its ultimate destination is the intergalactic medium, the incredibly thin, almost perfect vacuum that fills the vast spaces between galaxies. This medium is not entirely empty. It contains wisps of primordial hydrogen and helium, leftovers from the Big Bang, existing at temperatures just a few degrees above absolute zero. When the Cartwheel's superwind slams into this cold, tenuous gas, the effect is profound. The incoming blast of high-energy particles and hot plasma collides with the intergalactic material, shocking it and heating it to temperatures of millions of degrees. This is intergalactic medium heating, a process where a single, violent galaxy can raise the temperature of its cosmic neighborhood for hundreds of thousands of light years in every direction. The cartwheel becomes a cosmic hearth, its traumatic rebirth warming the void around it. This outflow has a dual legacy. On one hand, it pollutes the pristine intergalactic space with heavy elements like oxygen, carbon, and iron, seeding future generations of stars and planets with the building blocks of complexity. On the other, it represents a permanent loss. The gas blown away into the void is fuel that can never fall back to form new stars within the cartwheel itself. The galaxy's spectacular starburst is therefore a self-limiting event, its most violent act simultaneously seeding the cosmos and starving its own future, a testament to the fact that even on the grandest scales, creation and loss are forever intertwined. Amidst this stellar chaos, could entire worlds be taking shape? The super-star clusters blazing in the cartwheel's ring are not just stellar factories. They are potential planetary forges, where the same violent processes that birth stars might also be sculpting new solar systems. This possibility forces us to reconsider the very recipe for planet formation. In our own quiet galactic neighborhood, planets coalesce gently within the calm, dusty disks surrounding young stars over millions of years of relative peace. The environment inside a cartwheel supercluster is the polar opposite. Here, protoplanetary disks of gas and dust would be bathed in a relentless hurricane of ultraviolet radiation from thousands of neighboring stellar giants. This intense glare acts like a cosmic blowtorch, threatening to evaporate the lighter gases in a disk before they can clump together, potentially stripping away the material needed to form gas giants like Jupiter. Even more disruptive are the shock waves from nearby supernova, which could rip through a fledgling planetary system like a tidal wave, scattering its carefully accumulating dust and pebbles back into the void. The formation of rocky, Earth-like worlds in such a place seems an almost impossible feat. Yet nature is resilient. These disks might form much faster under extreme pressure, or they might hide in the dense, shadowed cores of their own swirling material, shielded from the worst of the external fury. Planets that do manage to coalesce would be born into a perpetual apocalypse. Their skies would be lit not by one sun, but by dozens of neighboring stars, creating a permanent, searing daylight. The night would be a rare event, perhaps occurring only when the planet's orbit carried it into the brief shadow of its own star. The cosmic weather report would be dire, with frequent sterilizing radiation storms and the ever-present threat of a nearby star-going supernova, an event that could scour a young world's atmosphere clean in an instant. So while the cartwheel's ring may indeed be forging planets, they would be unlike any we can comfortably imagine, born in a trial by fire that makes our own solar system's origins seem like a serene and sheltered garden. The cartwheel's perfect ring is an illusion, a beautiful lie told by distance. Zoom in, and a clear asymmetry emerges. One side of the luminous circle blazes noticeably brighter and more densely packed with stellar knots than the other. This imbalance is not a trick of the light, it is a direct imprint of the collision's chaotic physics. The gravitational shockwave that ignited the starburst did not expand into a uniform, pristine environment. The original spiral galaxy's gas was already clumpy and uneven, distributed in swirling arms of varying density. When the intruder punched through, it did not create a perfectly symmetrical splash. It sent a wave racing through this pre-existing landscape of hills and valleys. The brighter, more active side of the ring likely marks where the shockwave encountered an especially dense, massive cloud of primordial hydrogen. Think of an ocean wave hitting a coastal reef. Where it meets shallow, rocky ground, the water piles up into a towering, crashing crest of white foam. Where it travels over deeper water, it remains a smoother, lower swell. In the Cartwheel, the shockwave behaves similarly, compressing that dense gas cloud with extraordinary force, igniting a supercharged starburst that outshines the rest of the ring. But the intruder's influence did not end with the initial punch. The smaller galaxy, now receding, and its larger companion continue to exert their gravitational pull. This persistent tugging can act like a lens, subtly bending and focusing the outward propagating wave, channeling more energy and material toward one particular arc of the ring. It is as if the very hand that threw the stone is now gently guiding the ripples, ensuring one side of the pond remains more disturbed than the rest. This lopsided activity has profound consequences. It means the galaxy's rebirth is not a uniform process, but a staggered, patchy transformation. One sector is burning through its stellar fuel at a ferocious, unsustainable rate, while other sections of the ring may be conserving their resources for a longer, slower evolution. The asymmetry is a frozen moment of decision, showing us how random pre-existing conditions and ongoing external forces collaborate to write the final, uneven script of a galactic rebirth. Buried beneath the brilliant ring and the faint spokes lies a phantom, the ghost of the galaxy that once was. Using the most advanced image processing techniques, astronomers act as cosmic archaeologists, digitally peeling back the layers of trauma to reconstruct the Cartwheel's original face. They start with what remains, the scattered older stars in the faint halo and those dim, yellow populations within the skeletal spokes. By carefully mapping the motions and distributions of these stellar survivors, they can run the clock backwards, simulating how gravity would have gathered them before the intruder's violent passage. The emerging portrait is of a majestic, grand design spiral, likely similar in size and structure to our own Milky Way. It probably possessed sweeping, well-defined arms curving gracefully around a bright, prominent central bulge, a classic pinwheel of stars and dust rotating in serene balance. This forensic baseline is crucial, for it reveals the staggering magnitude of the transformation. That serene spiral, perhaps 100,000 light-years across, was not merely dented or warped. Its entire architecture was erased and rewritten. The brilliant central metropolis was scattered, its dense core reduced to a faint, off-center ghost. The elegant spiral arms were stretched into radial filaments and then overwritten by a propagating ring of fire 50% larger than the original galaxy itself. Understanding what was lost makes the spectacle we see today even more profound. It transforms the Cartwheel from a curious oddity into a measured before and after snapshot, allowing us to fully appreciate the cosmic energy required to turn a stately spiral into a celestial bullseye. This ghostly reconstruction is more than a technical exercise. It is an act of remembrance, ensuring we see not just the stunning result of the collision, but also the beautiful galaxy that was sacrificed to create it. The chaotic ring is also a natural particle accelerator of staggering power. Those countless supernovae and their expanding remnants act as cosmic cyclotrons, taking charged particles like protons and electrons and whipping them to velocities approaching the speed of light. These are cosmic rays, atomic nuclei stripped of their electrons and hurled across the universe. We cannot trace a single cosmic ray back to the Cartwheel Galaxy from Earth, as their paths are scrambled by the tangled magnetic fields of intergalactic space. Yet, based on the sheer violence of its starburst, astronomers classify it as a prime candidate source for these mysterious high-energy visitors. The process is relentless. Each supernova explosion creates a rapidly expanding shockwave, a moving wall of energy that plows through the surrounding interstellar gas. Protons and electrons caught in front of this wall become trapped, bouncing back and forth across the shock front like ping-pong balls in a cosmic game. With each crossing, the magnetic fields within the shock transfer a little more energy to them, accelerating them further until they finally break free, ejected into the void with unimaginable force. A single supernova can do this, but the Cartwheel's ring hosts thousands in quick succession. The overlapping shockwaves from multiple explosions create a turbulent, sustained environment where particles can be reaccelerated over and over, gaining even more energy before their final escape. These particles then embark on an eons-long journey, weaving through the magnetic labyrinths of galaxies and the vast voids between them. Some may eventually, billions of years from now, reach our own Milky Way, where they will slam into the upper atmosphere, creating a shower of secondary particles we can detect on the ground. While we can never know for certain which cosmic ray came from which galaxy, the Cartwheel stands as a template, a brilliant example of the kind of celestial engine required to forge the universe's most energetic natural projectiles. The galaxy's current brilliance is a fleeting chapter in a story spanning billions of years. That iconic blue ring powered by massive, short-lived stars is destined to fade. The most luminous of these stellar giants may shine with the power of millions of suns, but they are cosmic spendthrifts exhausting their nuclear fuel in just a few million years. Their spectacular lives end not with a whimper, but in supernova explosions that scatter their ashes. As these blue titans vanish one by one, the stellar population of the ring will undergo a profound shift. The stars that remain will be the smaller, more frugal ones, the red dwarfs and sun-like stars that can burn steadily for tens of billions of years. Without the intense blue glare of the young giants to dominate the light, the overall color of the ring will slowly, inexorably redden. It will transition from that searing electric blue to a softer whitish yellow, and finally to a dull, ruddy glow. This color evolution is the galactic clock ticking in slow motion. Over the next several 100 million years, the Cartwheel's most famous feature will dim and change hue, like a neon sign slowly powering down. The galaxy will not go dark, but its character will be utterly transformed. The furious starburst that defines it today will become a quiet, aging stellar community, its violent youth recorded only in the cooler light of its long-lived survivors. The bulge may still be visible in the distribution of stars, but its fiery, youthful passion will have cooled into the gentle, red embers of cosmic middle age. Yet from the wreckage of the collision, entirely new worlds may be assembling. The immense tidal forces that stretched the galaxy's arms into faint spokes and scattered stars into a vast halo also performed a more delicate act of cosmic sculpting. In the chaotic streams of debris, particularly where the expelled gas and dust are densest, gravity can begin a new work. It can gather these orphaned materials, pulling them into clumps massive enough to become self-gravitating islands. These are not mere clouds, they are potential tidal dwarf galaxies, infant stellar systems being born from the ruins of their parents' catastrophe. The process mirrors the formation of the first galaxies in the early universe, but on a smaller, more intimate scale. As the tidal debris expands and cools, the densest pockets within it start to collapse under their own gravity. Within these knots, star formation ignites, binding the gas and new stars together into a cohesive miniature galaxy. Unlike the main Cartwheel ring, where star birth is a frantic, supernova-driven frenzy, the formation of a tidal dwarf could be a slower, more isolated process. It would be a galactic offspring, a satellite born not from the primordial gas of the cosmos, but from the recycled, enriched material of a galactic disaster. This material is already seasoned with heavy elements forged in the Cartwheel's previous generations of stars, meaning any planets that later form within this dwarf galaxy would start with a rich supply of the building blocks for complexity. But could these clumps truly survive as independent galaxies? The forces working against them are formidable. They are born with very little, if any, of the mysterious dark matter that provides the gravitational glue for normal galaxies. Their binding strength comes almost entirely from the visible mass of their gas and stars, making them fragile, susceptible to being torn apart again by the continued gravitational tug of the massive Cartwheel or its companion galaxies. They would be cosmic ephemera, delicate and temporary, Yet, if they can gather enough mass and achieve a stable orbit at a safe distance, they might persist for billions of years, becoming permanent moons to the Great Ring. They would be living fossils, their very existence a direct, tangible piece of the collision, orbiting the cartwheel like children, forever circling the site of a transformative family event. Their study would offer a unique chance to watch a galaxy from its very first moments, built from the ground up with a known history and a known set of ingredients. Each potential tidal dwarf is a question hanging in the halo, a test of whether destruction on such a scale must always be an end, or whether it can also be a truly creative beginning, seeding entirely new futures into the darkness. The night sky from within a super-star cluster would be a spectacle of terrifying beauty, a permanent celestial festival of light that would render the very concept of darkness obsolete. Forget a single moon or a scattering of familiar constellations. Here, your world orbits a single star, but that star is merely one brilliant citizen in a dense metropolis of suns. The nearest stellar neighbors could be so close they appear not as points of light, but as resolved disks, rivaling our own sun in apparent size and bathing the landscape in a continuous, multi-directional twilight. Their combined light would be hundreds or even thousands of times brighter than a full moon on Earth, casting sharp, confusing shadows that shift and merge as the stars move in their intricate orbits. The sky itself would be a tapestry of color, streaked with the glowing pink and red curtains of vast emission nebulae, the energized gas clouds that birthed this stellar family. These nebulae would not be faint, distant smudges, but dominant structures, great luminous rivers and caverns that occlude whole sections of the heavens. Supernova would not be rare, once-in-a-lifetime events reported by distant astronomers. They would be a recurring hazard. Every few decades or centuries, one of the cluster's massive stars would reach its end. For a few weeks, a new, impossibly brilliant star would ignite in the sky, outshining all others, visible even in the perpetual daytime glow. This would not be a cause for wonder, but for dread, as the accompanying blast of radiation and high-energy particles could scour atmospheres and trigger mass extinctions. The cosmic weather report would be a constant warning of lethal stellar winds and gamma-ray bursts from unstable neighbors. Life, if it could arise in such a cauldron, would face a perpetual trial, evolving under a sky that is both breathtakingly magnificent and fundamentally hostile, a constant reminder that it was born in the very heart of the galaxy's most violent creative engine. The galaxy's own light is not the only way to probe its secrets. Far behind the cartwheel, billions of light years more distant, quasars burn with the ferocious intensity of supermassive black holes feasting on matter. If by a perfect cosmic alignment, the light from one of these brilliant beacons passes directly through the cartwheel's sprawling ring of gas and dust on its journey to us, it becomes the ultimate diagnostic tool. This is absorption line spectroscopy, a technique that turns a quasar's pure, white light into a detailed chemical fingerprint of everything it has passed through. As the quasar's light pierces the cartwheel's interstellar clouds, specific atoms and molecules within that gas grab onto tiny slices of the light, absorbing very specific colors corresponding to their unique identities. It is as if the galaxy's gas imprints its own barcode onto the quasar's beam. When astronomers finally capture that light with their telescopes and spread it into a spectrum, they do not see a clean, continuous rainbow. They see a pattern of dark lines like the missing teeth in a comb, each one representing an atom of hydrogen, a molecule of carbon monoxide, or an ion of iron that stole a piece of the light. The depth and width of each line tells a story. A very deep, broad line suggests a thick, turbulent cloud, packed with that particular element and churning with violent motion. A sharp, narrow line might indicate a colder, more quiescent wisp of gas. By analyzing this pattern, scientists can take a remote core sample of the cartwheel's interstellar medium without ever touching it. They can measure not just what the gas is made of, but its temperature, density, and even how fast it is moving relative to the quasar. This is crucial for understanding the true state of the ring. Is the gas predominantly hot and ionized, blasted by stellar radiation, or are there still significant pockets of cold, quiet fuel hiding between the stellar fireworks? The alignment of a background quasar would provide a direct answer, cutting a clean, single line through the chaos and giving us a pure reading of the galaxy's lifeblood at one precise location. It transforms a distant, unrelated object into a brilliant flashlight, shining through the cosmic fog and revealing its hidden structure in exquisite forensic detail. Its lonely portrait is a cosmic illusion. The Cartwheel Galaxy is not a solitary wanderer. It is the namesake member of a small, gravitationally bound family known as the Cartwheel Group. This celestial ensemble includes the two smaller companion galaxies we see so clearly in its iconic images, and likely a few other fainter dwarf galaxies, all dancing together through the void, bound by their mutual gravity over billions of years. This context changes everything. The catastrophic collision was not a random drive-by shooting in an empty universe. It was a violent family dispute, a clash between siblings who have lived together for eons and will continue to influence each other's destinies forever. The dynamics of this small group are a slow-motion ballet of immense forces. The galaxies orbit a common center of mass, their paths shaped by the total gravitational pull of the group, which is dominated by its unseen dark matter halo. The Cartwheel, for all its spectacular brilliance, may not be the dominant gravitational anchor. Its two companions, particularly the larger one, hold significant mass of their own. This means the Cartwheel is not simply sitting still, recovering from a wound. It is itself in motion, likely swinging around the group's center, its own trajectory subtly curved by the constant pull of its neighbors. This ongoing dance has profound implications. The gravitational tides from the companions did not end with the initial impact. They persist, continuously stretching and stirring the Cartwheel's delicate structures. Those faint spokes are not just relics, they are being gently pulled and twisted even now. The lopsided brightness of the ring could be influenced by this eternal gravitational nudge, focusing energy toward one side. And crucially, this group dynamic holds the key to the future. Is the smaller intruder on a runaway escape trajectory, or is it on a long, elliptical orbit that will bring it back for another encounter? The answer depends entirely on the total mass and energy of the entire Cartwheel group. Only by understanding the group's choreography can we predict whether the brilliant ring is a one-time spectacle or merely the first act in a longer saga of gravitational encounters. So the Cartwheel's stunning beauty is not a solo performance. It is the most dramatic scene in an ongoing galactic family drama, its fate forever tied to the quiet, persistent pull of its celestial siblings. This furious creation carries the seeds of its own end. The very stars blazing to life within the Cartwheel's ring are already beginning to dismantle the nursery that birthed them, a process astrophysicists call stellar feedback. It is the universe's ultimate balancing act, a self-regulating mechanism where star formation, in its greatest frenzy, eventually sows the conditions for its own cessation. The process begins with those massive blue giants. From the moment they ignite, they flood their surroundings with a hurricane of ultraviolet radiation and powerful stellar winds, streams of charged particles that roar outward at millions of miles per hour. This relentless energy barrage pushes against the surrounding clouds of cold gas, the very raw material for future stars, heating it and blowing it away like cosmic sand before a gale. But the true demolition crew arrives when these massive stars die. Their spectacular supernova explosions deliver a final titanic shockwave, injecting immense energy and turbulence into the interstellar medium. The combined effect of thousands of such explosions across the ring is to carve out those vast superbubbles, clearing huge regions of space and leaving behind hot, thin, high-pressure gas that actively resists further gravitational collapse. This hot gas acts as a formidable barrier. It prevents the remaining cold, dense gas clouds from coming together to form new stars. Essentially, one generation of stars literally blows away the fuel supply for the next. So where is the cartwheel in this cycle? Is it at the absolute peak of its starburst, or is feedback already beginning to quiet the storm? The evidence suggests it is in a transitional, self-limiting phase. We see the brilliant hotspots, sure signs of ongoing, frantic creation. But we also see the expanding superbubbles and the powerful galactic superwind, clear signatures that feedback is already in full swing, actively dispersing gas and quenching star formation in localized regions. The ring is not a uniform engine. It is a patchwork of construction and demolition sites operating side by side. Some knots are compressing and igniting, while adjacent areas are being evacuated and silenced. This means the galaxy's most spectacular era is inherently unsustainable. The current starburst is burning through its fuel at a breakneck pace, and the feedback from that very activity ensures the fuel will not be replenished quickly enough to maintain the fury. The cartwheel is caught in the act of its own magnificent undoing, a brilliant phoenix whose flames are so hot they threaten to consume the very ashes from which it rose. Somewhere between the brilliant ring and the faint halo, there may be another ghostly structure spinning at a right angle to everything else. A handful of observations hint at the possible existence of a polar ring, a delicate band of stars and gas orbiting over the galactic poles, tracing a path perpendicular to the main starburst disk. This would be an architectural marvel atop an already bizarre galaxy, like finding a second tilted hula hoop circling a spinning wheel. Polar rings are thought to be the trophies of a different kind of cosmic theft, not a direct collision but a slow, careful accretion. The theory suggests that long after the initial catastrophe, or perhaps even before it, the cartwheel may have gently captured and dismantled a smaller, gas-rich dwarf galaxy. As this victim was torn apart by tidal forces, its material would not settle into the existing plane of the galaxy, but instead, under specific gravitational conditions, it could have been funneled into a stable orbit crossing over the poles. Imagine pouring a thin stream of glitter onto a spinning plate from directly above. The glitter would naturally settle into a ring that circles the plate's rim from top to bottom, not around its edge. If real, this polar ring would be a fossil of a separate, quieter act of galactic cannibalism, a second chapter of acquisition written in faint starlight. Its stars would be old and its gas cold, a stark contrast to the youthful inferno of the main starburst ring. Confirming its existence is a monumental challenge, as its faint glow is lost in the glare of the cartwheel's brilliant primary structures. But if future, ultra-sensitive surveys do find it, the story of this galaxy becomes exponentially more complex. It would mean the cartwheel is not just a product of one violent impact, but a cosmic collector, a galaxy that has grown through both catastrophic trauma and slow, steady assimilation, weaving multiple histories into its single, stunning form. Every beautiful image of the Cartwheel Galaxy hides a fundamental, frustrating uncertainty. We see its perfect ring, its brilliant knots, its ghostly spokes, but to truly know this galaxy, we must answer a deceptively simple question: how far away is it? This is not just a matter of cosmic geography, it is the foundation for every other measurement we make. A slight error in distance can warp our entire understanding of the galaxy's true nature. Think of a streetlight on a foggy night. If you misjudge whether it is 50 feet away or 500, you will wildly miscalculate its true brightness and its actual size. The cartwheel is our cosmic streetlight, and the fog is the vast emptiness of intergalactic space. Astronomers have two primary tools to cut through this fog. The first relies on cosmic lighthouses within the galaxy itself, pulsating stars called Cepheids variables. These stars brighten and dim with a precise clockwork rhythm, and the period of their pulsation is directly tied to their true intrinsic brightness. By measuring how bright they appear to us and comparing that to how bright we know they truly are, we can calculate their distance like a standard candle. Finding Cepheids in the Cartwheel is a monumental task, as its distance pushes our telescopes to their limits, but it provides a direct step-by-step measurement. The second, broader method uses the galaxy's redshift. As the universe expands, it stretches the light from distant galaxies, shifting it toward the red end of the spectrum. The greater the redshift, the faster the galaxy is receding from us, and in our expanding universe, that speed correlates with distance, but here lies the rub. The redshift gives us a good estimate, but it can be influenced by local motions. The Cartwheel is not just drifting with the cosmic expansion, it is also being tugged by the gravity of its own group of galaxies, adding a small but significant uncertainty to its recessional velocity. The current best estimates place the Cartwheel at about 500 million light-years away, but that number comes with a margin of error that can be tens of millions of light-years in either direction. This seemingly small fudge factor has enormous consequences. If the galaxy is closer than we think, it is physically smaller and less luminous, meaning its starburst, while still spectacular, is less energetically monstrous. If it is farther, then the ring is even more immense, and the stellar factories within it are releasing even more staggering amounts of energy than our current models allow. Every derived property, from the total mass of its stars to the ferocity of its star formation rate, hinges on this one fragile number. The Cartwheel's distance is the master key, and until we turn it with absolute certainty, part of its magnificent story remains tantalizingly out of focus. The frantic starburst within the Cartwheel's ring offers more than a spectacle. It is a fundamental test of cosmic physics. For decades, astronomers have studied galaxies like our own Milky Way and derived elegant mathematical relationships, universal laws that seem to govern how efficiently a cloud of gas turns itself into stars. These laws are the rulebook for cosmic creation, describing how the density and pressure of gas influence the pace of stellar birth. But these rules were written in the quiet libraries of normal galaxies. The Cartwheel throws that rulebook into a hurricane. Its ring is a place of extremes where gas is not just dense, it is savagely compressed by a propagating shockwave. Where turbulence is not a gentle stirring but a maelstrom driven by supernova. Where radiation and magnetic fields are amplified to levels rarely seen in the modern universe. This raises a profound question. Do the same gentle laws of star formation apply in this cosmic war zone, or does chaos rewrite the rules entirely? To find out, scientists treat the Cartwheel's ring as a colossal natural experiment. They take their standard equations, the ones that work so well for the Milky Way's serene spiral arms, and they plug in the extreme conditions measured in the Cartwheel. They input the incredible densities of the gas clouds within the hotspot complexes, the blistering intensity of the ambient radiation field, and the supersonic speeds of the turbulent motions. Then they predict, based on the old rules, how many stars should be forming. The next step is to look through the telescope and count the actual number of newborn stars, using the glow of ionized hydrogen and the heat from dust as their guides. The results are telling us that the universe might have a second, more aggressive mode of operation. Preliminary evidence suggests that in the Cartwheel, star formation is not just faster, it is more efficient. The violent compression of the shockwave seems to squeeze more stars out of the same amount of gas, and it does so at a breakneck pace that the calm equations struggle to predict. This deviation is a clue to something deeper. It hints that under such extreme duress, the process itself may change. In a normal cloud, star formation is a slow, inefficient battle between gravity pulling material inward and magnetic fields and turbulence propping it up. Only a tiny percentage of a cloud's mass, maybe 1 or 2%, ever makes it into stars before feedback blows the rest away. But in the Cartwheel's ring, the shockwave tips the scales decisively in gravity's favor. It compresses the gas so suddenly and so severely that magnetic support may be overwhelmed, and turbulent motions might actually help rather than hinder the collapse, creating a frantic scramble where a much larger fraction of the gas, perhaps 10% or more, rapidly condenses into stars before any feedback can stop it. The galaxy becomes a factory operating at peak efficiency, where the assembly line runs so fast it defies the standard safety protocols. Understanding this extreme mode is not just about one galaxy. It is a window into the universe's most prolific eras. In the distant past, during the cosmic noon over 10 billion years ago, most galaxies were undergoing similar bursts of frantic activity, fueled by frequent collisions and abundant gas. If the cartwheel shows us that the standard laws break down under pressure, then our entire picture of how the universe built its first generations of stars and galaxies may need revision. The beautiful, chaotic ring is therefore a calibration point. By measuring exactly how much its star formation deviates from the quiet rules of our neighborhood, we can adjust our models for the ancient cosmos. This single galaxy, with its perfect bullseye, acts as a tuning fork for the universe's most violent symphonies of creation, letting us hear the true, deafening tempo at which stars were born when everything was young, hot, and desperate to shine. But the galaxy's hollow heart may hide a sleeping giant. At the very center of the cartwheel, where the ancient bulge was scattered, a supermassive black hole almost certainly resides, as it does in most large galaxies. Its current state, however, is one of the deepest mysteries. The collision that tore the galaxy apart should have been a feast of cosmic proportions. As the smaller intruder plunged through the core, its gravity would have violently stirred the gas and stars there, funneling unimaginable amounts of material directly toward the waiting black hole. In other galaxies, such an event triggers a quasar, a cataclysm of light as the infalling gas forms a searing, spinning disk of plasma, glowing with the brightness of 1 trillion suns before being swallowed. The cartwheel must have experienced this, a brilliant flash at its core that would have outshone the entire starburst-ring for a brief, spectacular era. Yet today, that core is quiet. Our telescopes detect no telltale X-ray scream or brilliant radio jet signaling an active, feeding monster. This presents a fascinating puzzle. Did the black hole gorge itself so completely during the collision that it cleared its immediate surroundings, leaving it starved and dormant in the aftermath? Or is it still feeding, but in a much more subdued, inefficient way, perhaps on a thin trickle of gas that managed to fall back toward the center after the initial chaos? The answer lies in the intricate dynamics of the post-impact core. The gravitational shockwave that raced outward to form the ring also acted as a cosmic vacuum cleaner, pulling vast amounts of gas away from the central region and hurling it into the outer disk. This may have left the black hole stranded in a relative desert, a king without a kingdom. Even as a banquet rages in the distant ring, its silence is a powerful clue. It tells us that the collision was so effective at redistributing the galaxy's mass that it not only destroyed the old stellar bulge, but also cut off the central engine's primary fuel line. The black hole's dormancy is a direct consequence of the same violence that ignited the ring, a reminder that cosmic upheaval can both create and starve the most powerful forces in the universe. The brilliant infrared glow is not a uniform blanket of warmth. Within that fiery haze, deeper shadows lurk, cold knots so dense they blot out the very heat behind them. These are infrared dark clouds, and they represent a crucial, hidden phase in the galaxy's ongoing story. While the rest of the ring blazes with the light of current creation, these clouds are the silent, dark nurseries where the next generation of stars is beginning to coalesce. They appear as Inkai silhouettes against the bright infrared background, not because they are empty, but because they are so incredibly thick with cold dust and molecular gas that they absorb all the warmth radiating from the surrounding stellar nurseries. Imagine holding your hand in front of a blazing fireplace. Your hand blocks the heat and light, creating a cold, dark shape against the orange glow. On a galactic scale, that is precisely what these clouds are doing, their immense density creating temporary cosmic shadows within the ring's inferno. Inside these frigid vaults, temperatures can plummet to just a few tens of degrees above absolute zero. This cold is the essential ingredient. It allows gravity to overcome the internal gas pressure that would otherwise keep a cloud puffed up and stable. As these dark clouds radiate away their scant heat, they begin to shrink, fragmenting into ever denser cores. Within these cores, the final, decisive battle between gravity and every other force is quietly being won, setting the stage for protostars to flicker to life. So the Cartwheel spectacle is not a single, monolithic event. It is a layered process where the furious light of the present is actively casting the dark, cold shadows that will become its future. These infrared dark clouds are the galaxy's way of investing in tomorrow, setting aside reserves of raw material that will ignite long after the current blue giants have faded into supernova remnants. They are the quiet, patient counterpoint to the ring's deafening roar, proving that even in the heart of chaos, the universe is always planning its next move. The Cartwheel's perfect ring is not a permanent fixture, it is a moving frontier. To our eyes, and even to telescopes comparing images taken decades apart, that brilliant blue circle appears perfectly still, a frozen splash in the cosmic pond. But this is an illusion of scale and time. The shockwave that sculpted it is still traveling, expanding outward from the galactic center at over 200,000 miles per hour. On the vast stage of the galaxy, this motion is real and measurable, a phenomenon astronomers call proper motion. This is not the galaxy's overall drift through space, but the specific internal movement of the ring structure itself, its slow creep away from the hollow core. Detecting this motion is one of the ultimate observational challenges in astronomy. It would require comparing exquisitely precise positions of specific star clusters or gas clouds within the ring over a very long baseline of time, perhaps using a space observatory positioned with incredible stability or a network of radio telescopes spanning the solar system. The goal would be to see, over maybe a human lifetime, a minuscule shift, a displacement smaller than the width of a human hair seen from a mile away. Yet the scientific payoff would be monumental. A direct measurement of the ring's proper motion would act as a cosmic stopwatch. By knowing exactly how fast the ring is expanding and measuring its current radius, astronomers could run the clock backward with perfect precision. They could calculate the exact moment to within a few million years when the shockwave began its journey from the center, which is the precise moment of the catastrophic collision. This would pin a firm date on the galaxy's violent rebirth, transforming its history from an estimate based on models into a directly observed fact. It would tell us not just that the collision happened, but exactly when, allowing us to place this spectacular event on a precise timeline of cosmic history and understand what the universe was doing elsewhere when this galactic wheel was set into motion. But our telescopes may be missing a hidden ocean of fuel. The brilliant ring glows with the light of newborn stars, and the cold dust silhouettes tell us where more stars are beginning to form. Yet between these two extremes, there could be a vast, invisible reservoir of material that our conventional tools simply cannot see. This is the concept of dark gas, a theoretical component that could make up a staggering portion of the Cartwheel's mass and hold the key to its long-term future. When astronomers map the galaxy's fuel supply, they rely on proxies. They look for the radio signature of carbon monoxide, a molecule that typically traces the locations of cold molecular hydrogen, the primary ingredient for star formation. They also measure the infrared glow of dust which is mixed in with that gas. But what if significant clouds of molecular hydrogen exist without their usual tracers? This is dark gas hydrogen molecules that have not yet partnered with carbon atoms to form carbon monoxide, or that float in regions too diffuse for dust to have formed. It is the universe's ultimate stealth material, cold, neutral, and nearly impossible to detect directly. In a chaotic environment like the Cartwheel's ring, where a violent shockwave has just ripped through, such conditions are not just possible, they are likely. The collision could have shredded and dispersed gas clouds before they had time to form complex molecules or accumulate dust, leaving behind a pervasive fog of pure molecular hydrogen that our carbon monoxide surveys completely miss. This unseen ocean would be a game-changer for our understanding. It means the galaxy's ring could be far more massive with raw fuel than our current maps suggest. All those models predicting the starburst will soon exhaust itself might be profoundly wrong. Instead of running on fumes, the Cartwheel could be sitting atop a deep, hidden well of hydrogen, a secret stockpile that could keep its stellar factories running for hundreds of millions of years longer than anyone has dared to predict. The dark gas would not just extend the show, it would also solve a puzzle. The observed rate of star formation in the ring, as furious as it is, might still be lower than what the shockwave's compression should theoretically allow. Where is the bottleneck? Perhaps it is not a bottleneck at all, but a mismeasurement. If a large fraction of the fuel is hiding in this dark form, then the true density of the ring is higher, and the star formation efficiency might actually align with the extreme physics of the shockwave. Finding this ghostly reservoir is one of the great observational quests for the next generation of telescopes. It requires looking for the most subtle of signatures, perhaps a faint, specific ultraviolet absorption line from molecular hydrogen, or an anomalous glow of gamma rays caused when cosmic rays interact with hidden gas clouds. Confirming its existence would not just rewrite the Cartwheel's future, it would reveal a hidden component of the cosmos itself, a silent, dark ocean in which all the brilliant islands of starbirth are merely the visible, shining tips. The Cartwheel Galaxy's secrets are waiting for an eye that can see through the dust. The James Webb Space Telescope, with its unprecedented infrared vision, is turning its gaze toward this cosmic bullseye, not just to take a prettier picture, but to answer fundamental questions that have lingered for decades. Its instruments are designed to dissect the galaxy's chaos with surgical precision, peeling back the obscuring veils to reveal processes we have only been able to theorize about. One of its primary missions is to stare straight into the heart of those brilliant superstar clusters, the hotspot complexes that blaze with newborn stars. Hubble gave us their brilliant outlines, but the thick dust they create often hides their earliest, most formative stages. Webb's infrared eyes can penetrate that dust, allowing astronomers to witness protostars in their cocoons, to see the swirling disks of material that may become planetary systems, and to measure the exact temperatures and masses of stars too young to shine in visible light. This will finally tell us if star formation in such an extreme environment follows the same gentle rules as in our Milky Way, or if the violent shockwave has rewritten the physics, creating stars faster and more efficiently than we thought possible. Beyond the stellar nurseries, Webb will perform a deep chemical analysis of the ring's gas. Every molecule absorbs and emits light at specific infrared fingerprints. By studying these spectral lines, Webb can create a detailed inventory of the Cartwheel's interstellar medium. It can measure the abundance of water ice, carbon dioxide, and complex hydrocarbons swirling in the ring. More importantly, it can trace the ratio of different elements like oxygen to iron with far greater accuracy than ever before. This chemical map will act as a forensic report on the starburst's history. It will show us exactly which types of supernova have already detonated, whether from massive stars or white dwarfs, and how thoroughly they have polluted their surroundings. We will see the enrichment process in real time, watching as the galaxy's traumatic rebirth forges the elemental building blocks for future planets and potentially life, and then scatters them into the void. Perhaps most exciting is Webb's ability to hunt for hidden stellar populations. The galaxy's faint, off-center core and those ghostly spokes are home to older, cooler stars that emit most of their light in the infrared. Webb can isolate their gentle glow from the blinding glare of the blue ring, allowing scientists to finally census this ancient population. By studying these stars, we can weigh the ghost of the original spiral galaxy with new precision, understanding exactly how much mass was in its central bulge before the collision tore it apart. Furthermore, Webb might discover entirely new structures, faint streams of stars, the tentative beginnings of tidal dwarf galaxies, or even that theorized polar ring, all hiding in the infrared shadows. Each discovery would add a new chapter to the galaxy's complex biography. The James Webb Space Telescope is not merely observing the Cartwheel Galaxy. It is interrogating it, using its powerful infrared vision to demand answers about the violent physics of creation, the chemical evolution of galaxies, and the hidden architecture that holds this magnificent wheel together. Its perfect ring and haunting beauty have escaped the confines of astronomy, becoming a symbol in our collective imagination. The Cartwheel Galaxy has spun its way into science fiction, its iconic form providing a ready-made backdrop for stories of cosmic wonder and alien grandeur. In countless digital artworks and book covers, it looms in the background of imagined star systems, a celestial landmark so striking it needs no explanation. It is the kind of place where advanced civilizations might build their megastructures, not just for function, but for a view that matches the scale of their ambition. Its form suggests both ancient catastrophe and ongoing creation, a duality that storytellers love. It is not a peaceful spiral like the Milky Way. It is a galaxy clearly shaped by immense violence, a perfect setting for tales of galactic empires rising from ruins or for cosmic mysteries that challenge the very laws of physics. When an author or filmmaker needs a visual shorthand for the truly alien, the deeply ancient, or the overwhelmingly powerful, the Cartwheel's unique silhouette does the work in an instant. It tells the audience that the characters are far from home, operating in a realm where the rules are different and the stakes are written in starlight. It becomes more than a setting, it is a character in itself, a silent, majestic witness to the dramas playing out in its luminous ring. This artistic adoption speaks to something deeper about how we process cosmic scale. The sheer size and distance of real galaxies can feel abstract, numbing in their immensity, but by placing a recognizable, beautiful, and bizarre object like the Cartwheel into a narrative, science fiction bridges that gap. It grounds the unimaginable. We can picture a starship navigating the faint spokes or a research outpost perched on a world within that brilliant blue ring, its sky forever lit by the glow of a million stellar nurseries. The galaxy provides a concrete stage for human or alien stories of exploration and survival. Its inherent strangeness raises immediate questions for any story. What would life be like inside a starburst-ring? Could a civilization survive the constant supernova and lethal radiation? Might the galaxy's twin companion worlds harbor ancient beings who witnessed the collision itself? The Cartwheel invites these speculative leaps, turning astrophysics into a playground for the imagination. It is a testament to the object's power that it fuels stories not just about what is, but about what could be, allowing us to project our hopes, fears, and curiosities onto its luminous canvas. Perhaps its most potent role in fiction is as a symbol. The galaxies form a perfect circle born from chaos, resonates with timeless themes. It can represent the cyclical nature of existence, where destruction is always followed by creation, and death gives birth to new stars. It can symbolize a cosmic reset, a civilization or a universe recovering from a cataclysm more profound than war, emerging in a new, radiant form. For a story about rebirth or renaissance, What better visual metaphor than a galaxy literally reforming itself from a traumatic impact? Conversely, its hollow center can symbolize loss, a grandeur that is beautiful but fundamentally empty, a warning about the price of transformative violence. Science fiction uses these symbols to explore not just outer space but inner space, using the galaxy's architecture to mirror psychological or societal states. A character journeying toward the Cartwheel's quiet core might be seeking answers in a place of ancient silence, while another racing along its fiery ring could represent a life lived at a frantic, unsustainable pace. The galaxy's duality gives storytellers a rich palette, its every feature, the ring, the spokes, the void carrying narrative weight. This cross-pollination between science and fiction is a feedback loop of inspiration. The real cartwheel, discovered and studied by astronomers, provides the awe-inspiring template. Artists and writers then take that template and extrapolate, filling its spaces with life, drama, and meaning. Their visions, in turn, inspire public fascination, drawing more eyes to the actual science. A viewer who first sees the cartwheel in a stunning sci-fi film might later seek out a Hubble image and from there fall into the rabbit hole of learning about galactic collisions, shockwaves, and stellar evolution. The fictional representation acts as a gateway, making the cold, hard facts of astrophysics feel personal, epic, and relevant. It transforms the galaxy from a data point in a catalogue into a place in our mental universe, a destination we have visited in our dreams long before our telescopes or probes could ever hope to reach it. In this way, the Cartwheel Galaxy achieves a rare status. It is both a rigorously studied scientific object and an enduring icon of the cosmic unknown, its true story forever intertwined with the fictional ones we tell about it. The Cartwheel Galaxy's distant light does not belong solely to professional observatories. It also shines in the dreams and hard drives of amateur astrophotographers across the planet. This cosmic bullseye, though nearly 500 million light-years away, has become a legendary trophy, a test of skill and patience for those who capture the universe from their own backyards. To image it is to join a quiet, global fellowship of night sky hunters, where success is measured in hours of collected starlight and the triumphant reveal of that faint, perfect ring emerging from the noise. The equipment required is not trivial, often involving sophisticated telescopes, sensitive cameras cooled to fight electronic noise, and mounts that can track the sky's rotation with flawless precision for an entire night or many nights in a row. The process is a marathon. An astrophotographer might spend dozens of hours over multiple weeks gathering countless individual exposures, each one a 5 or 10-minute snapshot of photons that began their journey before life crawled onto land on Earth. Then comes the meticulous digital development, stacking the images to reinforce the faint signal, carefully subtracting the sky's own glow, and teasing out color and detail from data that initially looks like a field of gray static. The final result is a personal masterpiece. These amateur portraits may lack the razor-sharp resolution of Hubble, but they possess a different kind of magic. They are filled with the texture of our own atmosphere, often showing the cartwheel nestled among the pinpoint stars of its own constellation, Sculptor, grounding its alien form in the familiar star patterns we can see with our own eyes. To look at such an image is to feel a direct connection, knowing that this breathtaking glimpse of a galactic cataclysm was captured not by a billion-dollar satellite, but by a dedicated individual under a dark sky, bridging an unimaginable gulf with technology, perseverance, and pure wonder. Each successful image is a celebration of human curiosity, proving that the drive to explore the cosmos is not confined to giant agencies, but lives powerfully in the quiet pursuit of a single person, patiently waiting for the universe to reveal its secrets, one photon at a time. This beautiful chaos may be a universe of spectacular, silent gardens, the Cartwheel Galaxy's furious starburst, while a breathtaking engine of creation, forces us to confront a sobering cosmic question. Could such a violent place ever be a home for life as we know it? The very processes that light up its brilliant ring likely render it a sterile wilderness on a galactic scale. Within those searing blue knots, the environment is apocalyptic. Newborn massive stars flood their surroundings with a constant, lethal bath of ultraviolet and X-ray radiation, a glare intense enough to break apart the complex molecules that are the precursors to biology. Even more devastating are the supernovae. Given the frantic star formation rate, these stellar explosions are not rare, catastrophic events spaced by millennia. They are a regular occurrence, perhaps every few decades in the most active sectors of the ring. Each detonation unleashes a wave of destructive energy that would sterilize entire planetary systems, scouring atmospheres and baking surfaces with radiation across distances of dozens of light years. A planet orbiting a star in such a region would have its evolutionary clock reset over and over, never granted the billions of years of stable, quiet conditions Earth enjoyed to allow life to arise, diversify, and grow complex. The concept of a galactic habitable zone, a region where conditions are favorable for life, seems to shrink to nothing within that luminous ring. It is a place of magnificent construction and immediate demolition, where the cosmic machinery operates with a brutality that leaves no room for the delicate, slow experiment of biology. This leads to a profound reflection on our search for extraterrestrial intelligence. Projects like SETI, the search for extraterrestrial intelligence, scan the cosmos for signals, often focusing on galaxies rich with stars. But the Cartwheel presents a cautionary tale. A galaxy can be spectacularly bright, energetically vibrant, and teeming with stellar activity, yet be utterly inhospitable to the development of any civilization capable of building a transmitter. Its brilliance could be a sign of cosmic infertility, a beacon that signals not life, but a prolonged and beautiful catastrophe. So while we marvel at its ring of fire, we might also be looking at a galactic graveyard for potential, a stunning monument to the fact that the universe's most creative forces are often its most destructive. The Cartwheel Galaxy is more than a cosmic object, it is a profound metaphor written in starlight. Its entire existence is a testament to a universal truth, that catastrophic upheaval can be the direct catalyst for breathtaking creativity and renewal. This galaxy shows us that destruction is not always an end, it can be a violent, necessary beginning. Before the collision, it was likely a serene, beautiful spiral, a cosmic masterpiece in its own right. But that state of quiet order was shattered by an unimaginable impact, an event that scattered its core and tore its arms apart. From that trauma, something new and spectacular emerged. The shockwave of the collision became a sculptor's hand, compressing gas and igniting a ring of stellar birth so intense it outshines the galaxy's entire past. The very violence that dismantled its old form provided the pressure and the raw materials to build its brilliant new identity. It did not merely recover, it transformed, becoming something entirely different and radiant, a phoenix forged not from fire but from gravitational chaos. This cosmic process mirrors the most powerful cycles of renewal we know. In nature, a forest fire, while devastating, clears the ground for new growth, releasing nutrients and allowing sunlight to reach seeds that would never have sprouted in the deep shade. In human experience, personal loss or societal fracture, while deeply painful, can often clear space for radical reinvention. The old structures, however comfortable, are swept away, and in that cleared space, under immense pressure, new ideas, new art, and new ways of living can ignite with a ferocity that would have been impossible under the weight of the previous order. The Cartwheel teaches us that periods of brilliant, prolific creation are often preceded by a shattering impact. Its luminous ring is a permanent reminder that from the deepest chaos can come the most focused light, that a perfect, beautiful circle can be the final shape of a catastrophe. But all rings must fade, and every starburst eventually exhausts its fuel. Billions of years from now, the Cartwheel Galaxy's defining spectacle will be a distant memory. That brilliant blue ring of fire, having raced outward for eons, will finally slow and dissipate. The last of its massive blue giants will have long since detonated, their ashes scattered into the cooling void. The superstar clusters will age and drift apart, their stellar cities dissolving as their gravitational bonds are loosened by countless close encounters. What remains will be a vast, diffused disk of older, redder stars, still tracing the ghostly outline of that once magnificent bullseye, but now glowing with the quiet, ruddy light of stellar retirement. The galaxy's current furious chapter of creation will be closed, its pages written in the fading light of countless dwarf stars that will burn steadily for trillions of years to come. Yet the story of its relationships continues. The twin companion galaxies, the possible architect of the collision and its larger sibling, are not done with their dance. Gravity is a patient force, and over timescales that dwarf human history, it continues to draw these celestial siblings together. The current trajectories suggest a slow but inevitable fate. Over the next several billion years, the Cartwheel and its companions will likely spiral inward, their mutual gravitational pull overcoming their momentum. They will not collide in another spectacular, ring-forming punch, but will instead engage in a slow, stately merger. Their stars, separated by vast distances, will rarely touch, but their dark matter halos and vast clouds of gas will intertwine, weaving the three separate galaxies into one. The final product of this grand unification will bear little resemblance to the wheel we see today. The elegant, delicate structures will be erased by the gravitational chaos of the merger. The faint spokes will be shredded, the last remnants of the ring will be smeared into a general haze, and the off-center core will be blended with the hearts of its companions. The galaxy will lose its flat, spinning disk entirely. What emerges from this calm, drawn-out collision will be a giant elliptical galaxy, a featureless, football-shaped swarm of ancient stars. It will be a cosmic retirement home, a serene and mostly silent island where star formation has ceased nearly completely, its gas supply long since expelled or consumed. The stellar population will be overwhelmingly old and red, with few, if any, new stars being born to light up the darkness. This elliptical galaxy will be larger and more massive than any of the original three, a testament to the slow, aggregating growth of galaxies over cosmic time. This ultimate fate transforms our understanding of the Cartwheel's beautiful present. Its spectacular ring is not a permanent state, but a brilliant, temporary flare in a life that spans tens of billions of years. We are witnessing it in its most dramatic, volatile, and creative phase, a fleeting adolescence of cosmic proportions. The violence that seems so defining is merely a punctuation mark in a much longer sentence. The galaxy spent its early life as a serene spiral. It is now in the brief, fiery throes of its starburst youth, and it will spend the overwhelming majority of its future as a quiet, featureless elder. Our ability to see it now, in this perfect bullseye moment, is a stroke of incredible cosmic timing. It is as if we looked at a human life and caught it precisely in the single, dazzling second of a fireworks display, missing the decades of calm that came before and will follow after. So the Cartwheel Galaxy is more than a list of 50 strange phenomena. It is a single, unified story of transformation. It shows us how chaos can forge perfect geometry, how destruction can fuel immense creation, and how even the most radiant and unique structures are merely waypoints in an endless journey of change. Its hollow core, its luminous ring, its dark spokes, and its wandering companions are all interconnected chapters in a biography written by gravity. To study it is to watch the universe in the act of rewriting itself, to see the raw, beautiful, and terrifying physics that govern the lives of galaxies. It stands as a permanent reminder that in the cosmos, beauty is often born from catastrophe, that order can emerge from violence, and that what we see is never the end of the story, but merely a breathtaking, transient page in an epic that has been unfolding for billions of years and will continue for billions more. From a hollow heart to a ring of fire, we have traveled through 50 astonishing secrets of this celestial wheel. Each one, from its ghostly spokes to its hidden dark matter, reveals a single, unified truth. The Cartwheel Galaxy is not merely a distant spectacle. It is a complete cosmic laboratory, a single experiment where the universe tests its most extreme physics. By studying its violent rebirth, we are granted a front-row seat to the forces that shaped not just this one galaxy, but every galaxy we see, including our own serene Milky Way. Its chaos holds a mirror to our past and a window into our future, showing us how beauty is forged in the crucible of catastrophe. So, as this journey concludes, we turn the question to you. Which of these 50 strange phenomena captured your imagination the most? Was it the monster black holes breaking all the rules, the possibility of planets born in perpetual apocalypse, or the ghostly echoes of the spiral that once was? Let us know in the comments below. If you enjoyed this deep dive into the mysteries of space, be sure to subscribe. We explore the universe's greatest wonders, one cosmic story at a time. And tonight, or any clear night, take a moment to step outside and look up. Somewhere in the vast darkness, that perfect cosmic wheel is still spinning, a silent, beautiful reminder of the endless, transformative drama unfolding in the deep